Okay, so good morning everyone. So let's start with where we left last time. So we were discussing configuration of a rod which is uniformly strained, right? By Vk. Okay, so it takes some shape, and what I mean is that it has same Vk everywhere. That's why I say it is uniform. Uniformly along the arc length only. Okay, and we found out the analytical formula for the center line, which was little r of s equals magnitude of v times cosine of phi times s times k hat plus sine of phi into 1 over magnitude of k into identity minus e to the power s k k hat cross k hat perp. Okay? And what we saw was that this term generates a straight line, whereas this term generates a circle, and the combination of these two then leads to a helix, right? So this generates a helix. And similarly, the rotation big R of s, we had found it to be e to the power s k. So these two are such that at s equal to 0, the cross section at s equal to 0 has its center at the origin, and the orientation of the cross section at s equal to 0 is along the axis of the coordinate system, right? Big R of s at s equal to 0 is identity. All right. So let's look at some particular cases. For example, if v is parallel to k, then what happens? So if v is parallel to k, sorry, this is parallel to k. You remember that phi was the angle between v and k. So if v is parallel to k, phi is 0, sin phi becomes 0, right? So only this term survives. So this center line then degenerates into a straight line. And can you think of some of the simplest situations where v and k are parallel? So if v is equal to 0, 0, v3 and k is equal to 0, 0, k3. So you can see this is the situation where v and k are parallel, right? And what does this correspond to? So it has got only stretching, no shear, and here you got only twist. So this corresponds to combined extension twist situation. So this is, so one example is combined extension torsion. Isn't it? So you have got a beam, you stretch it and twist it, the center line remains straight, and that's why that formula also tells you that center line will remain straight, right? So that was one particular situation. You think of another situation where V is perpendicular to K. So what's going to happen in this case? This term drops out, but only this survives. So the helix degenerates into a circle. And can you think of a deformation where this can happen? When are V and K perpendicular? What about pure bending, right? In case of pure bending, the center line is a circle, right? It's an arc of a circle. So V 0, 0, 1, pure bending, no shear, no stretch, whereas K could be K 1, 0, 0, right? Or you could also have K 1, K 2 together, still V and K are perpendicular to each other. So that's the case of pure bending. So one example here is your pure bending. Okay? And of course, if these two situations are not there, then you have the full helix, right? And last time we also wrote down this formula slightly differently, which was, we wrote it as little r of s equal to s times tau k hat plus identity minus e to the power s k into little x f. And then we had defined tau as v times cos phi, right? And this little x of f, so we had defined our tau as magnitude of v times cos phi, whereas this little x of f, you could see that is same as v cross k divided by magnitude of k square. And this is the formula for a helix in a standard form. This is called fixed point of the helix, fixed point. And this tau is related to pitch of the helix. You know, pitch meaning how much does the helix move along the axis when you make a full circle. Okay? So this tau is related to that. Can you, for example, find out what is the pitch of the helix in terms of tau? So maybe I should go to the next board. Okay, so what's the pitch of the helix? So how much s you have to move so that the helix takes a full turn? 2 pi. See, the rotation is given by this formula. So, how much should S be so that the angle here becomes 2 pi? For a given S, how much is the angle here? So, this is a rotation about k axis, and how much is the angle of rotation for a given S? So, you have to say S times magnitude of k, that is the angle of rotation of this rotation matrix, right. And this has to be equated to 2 pi. So, that means S is equal to 2 pi over magnitude of k. So, you then plug in your S over there and you see how much does it move along the k axis. So, the translation is S times tau. So, what is the pitch of the helix? So, that means pitch of the helix is simply this S, which is 2 pi over magnitude of k times tau, and tau is this phi cos phi. Right. So, that is the pitch of the helix. Is that okay? Right. See, you see the angle of rotation, this tells you the angle of rotation, isn't it? If you want to understand it more carefully, maybe the way to do this would be okay, you could write it also as little x of f plus 0 minus here plus e to the power s k into 0 minus little x of f plus s tau k hat. See, I wrote the same thing, little r of s as equal to this. This xf is present here, I times xf is your xf, plus you see this number negative of e to the power sk into little xf is present here, e to the power xk into negative of little xf plus the first term here. And what does the first two term tell you? This is simply the rotation of 0 vector about little xf by this rotation matrix. You see, if you have a point little x of f and you have the origin somewhere over here, and I want to rotate this origin, rotate this point about this point xf. And the rotation is such that the axis of rotation is along some k hat. So, what is going to happen? So, that is the, maybe we can make it like this. So, I want to rotate this vector so this is little x of f, and I want to rotate this vector about this axis. So, what would happen? It is going to do this, right? So, it is only this vector which is going to rotate such that its magnitude won't change. So, the final position would be what? Maybe this vector rotates and let us say it comes here, somewhere over here. So, this vector after rotation, that would be that rotation matrix times this vector, but you see this vector is 0 minus little x of f, because it is rotating about little x of f. So, it is minus little x of f. So, that is this vector. But what is the final position? This point moved here. So, the final position is this, which is this plus this, but this is this number, and you have to add this vector, which is same as little x of f. Right. So, the first two terms here is simply the rotation of the origin point, and this term is the translation. So, if I want to understand this more physically, then you would draw axis, okay, that's your E1, E2, E3, and your little x of f could be somewhere over here, and then your k vector unit vector k, and that is the origin. You see little r of s at s equal to 0 is equal to 0, isn't it? When you plug in s equal to 0, little r of s becomes 0. So, the center line is passing through the origin, right. So, it is definitely present here at s equal to 0. So, this term, it simply rotates this point, whereas that term is translating, isn't it? Okay. So, this term is rotating and then translating, and you see, so how much is the rotation? As the helix gets formed, Oh, it's really difficult to draw it here. Okay, so that's the helix. So you see, when does it make a turn of 2 pi? When it comes from here to here, right? And this is the pitch of the helix. When it makes one full turn, how much is the translation? That's the pitch of the helix. So to make one full turn, the s has to be 2 pi over magnitude of k. And so the translation is simply s times tau, which is in this number. Right? Okay?
Maybe quickly, I suppose that we had many people show again how we come from this cross product k hat perp.
Oh, to
plus
this.
all the four prefactors to v cross k.
Okay, okay, yeah, of course.
Just
sure, I can do that.
avoid repetition.
Maybe I can do it over here. This box. Okay, what you see over there, if I compare these two, what is my little x of f? It is magnitude of v sine phi k cross k perp divided by magnitude of k. So if I just simply compare this xf with what we have over there, okay, then what is k perp? K perp was perpendicular to k, right? Here is your k perp. So what do you think, what would be k perp then? You subtract the component of v along k, then it will point towards k perp, isn't it? V has got two components, one along k and one along k perp. So if you subtract the component of v along k, the remaining thing will point along k perp. So what's k perp going to be? That's v minus v dot k into k hat. And of course, you have to then divide by its magnitude, divide by some factor. And what else should we do? maybe we could find it some other way then. V cross k. So V cross k V cross k over magnitude of k square. So that's same as magnitude of V times magnitude of k times sine of phi, isn't it? And what's the direction of V cross k? That would be same as the direction of V divided by magnitude of V cross k perp. Which should be the same as, oh, we want to write in terms of k hat cross k hat perp. Yeah, because I want to compare this with this number.
Then you have it.
I have it.
Instead of the V.
K hat. Yes, of course. Yeah, that's right. Yeah, because they are perpendicular, so it's simply this.
They're all units.
Yeah, they are all unit. Okay, very good.
Uh,
No, they are both unit vectors.
No, the magnitude of k is you divide by that thing squared.
Okay, let me see again. So this number on the numerator, what's the magnitude of this number? It's V times k times sine of phi. So that's the magnitude. And what's the direction? The direction is perpendicular to V and k, which would be same as k hat cross k hat perp, because they are both unit vectors. So direction will be given by this number also, isn't it? So this takes care of the numerator, and then I divide by the denominator k squared, magnitude of k squared, and then you can see I get this. Okay. Yeah, that was not so easy. All right, so I hope we are clear about the pitch of the helix, isn't it? Similarly, you could also talk about the radius of the helix. What's the radius of the helix? Can you guess what's the radius of the helix? Yes? XF? Why do you think so? Of course, that's the whatever the circle is there, it should be radius of that circle. But for that, this XF must be perpendicular to k hat, isn't it? But it is by definition, if you see here, XF is perpendicular to k hat. So it's perpendicular to k hat, and the center line passes through the origin. So this also becomes the radius of the helix. So radius of the helix is same as the magnitude of XF, which is V sine phi divided by k, which is equal to V sine phi divided by k. Okay, so what we see is that the pitch of the helix, radius of the helix, they are all given by the strains V and k. So once you set your strain V and k, then the helix that is formed, all its parameters are given by the strain. It's V and K, radius, pitch, and anything else that you want to talk about. All right. So that was just the center line and the rotation. What about the whole rod itself? How will the whole rod look like? What would be the deformation map for the whole rod? So, if you look over here, your rod has become, the center line is in helix. So, then you have to put your cross section, isn't it? So, this is just a center line, you have to also put your cross section. And you know the S equal to 0 cross section, for example. How is the S equal to 0 cross section supposed to be put? It has to be put such that its center is at the origin and its orientation is identity. So, how should we put it here? It is going to be put over here, but the orientation, how should it be? In the plane of E1, E2, right? Because rotation is identity, its rotation is identity. So, it is same as in the straight configuration, and in the straight configuration the cross sections are in the E1, E2 plane, isn't it? So, here also it should be in the E1, E2 plane because its rotation is identity. So, we have to put it in the E1, E2 plane. Okay. So, we need to put it in the E1, E2 plane. It may not look like, but this is in the E1, E2 plane. Okay. But this is not plane, this is not normal planar, isn't it? Because we want to let it warp also. So, again you have to just bring that u. So, how will your deformation map look like? Little x of big X1, comma big X2, comma S. What is that going to become? That will be little r of S plus big R of S into, now if I just say X alpha E alpha, then that only makes your cross section planar, and then you introduce your u here, right, to let it warp, plus u of x1 x2 . So, that is your full deformation map, and where little r and big R are known to you through those analytical formula, isn't it? You could also combine these two together and you just say it is some little x of cross section at x equal to 0. So, you could also write this as little r of S plus big R of S times some little x of 0 cross section, which is only a function of x1 x2. So, both of them have been subsumed in this quantity. right? And let's see what do we get when we plug in these two formula, little r and big R. Okay. So little r is yeah, over there. Okay, so that's little xf plus e to the power sk of little x naught minus little xf plus s tau k hat. You see, I just wrote here little r of s from here, and this quantity rotation times little x naught. So this 0 I replaced with little x naught, because we have an extra term, you could always bring it here, isn't it? And then we have to analyze what does this mean physically. What does this mean physically now? Look at this term. What does this mean physically? Just as we were analyzing this term over here, you look at that term. So over here, this was rotation of the origin about the fixed point xf, but now this is rotation of x naught about the fixed point xf, where x naught is now your whole cross section. So now instead of just rotating the origin, which could only generate your center line, you have to now rotate the whole cross section about this point x naught, xf, and then let it also translate, and that generates your full rod, the full 3D rod, isn't it? So by only knowing this little x naught, if you can know this little x naught, how is the shape of the cross section at s equal to 0, you can use that map to generate the whole rod, isn't it? So this is the only unknown here. The s equal to 0 cross section, the shape of that cross section is the only unknown. If you can somehow know that, you can generate your full rod, right? And as you might guess, it's going to be about the center line. Okay. Okay. All right. So what should be the next step then? So you got your deformation map. So you see, it was not. So you could do some analytical calculation, isn't it? And could get some physical insight on what's happening when you subject a rod to uniform V and K. And you have to keep in mind that our goal is now to get your little x naught, the warping of the cross section for a given V and K. But once we have the deformation map, we know that we have to minimize the cross section energy, right. So, from deformation map we get your deformation gradient, then we will write down the energy of the cross section, and then you could minimize it. So, if that is my little x, what will be the deformation gradient big F? If you allow me to write, this is going to be e to the power s k V tensor product E3 plus k cross little x naught tensor product E3 plus del of little x naught over del big X alpha tensor product E alpha. You could use that second line over there, the second line over there, take the gradient and you would get this. I think we had also done it maybe last lecture or the lecture before. Okay, but basically you just have to take the gradient and you will then reach over here. Okay. Once we have the deformation gradient, how to get your little x naught? We know that little x naught would be such that the cross sectional energy should be minimum, right. That is the guiding principle to get the warping. So, we set our cross sectional energy, which is W of big F integrate over the cross section, and then you minimize this over little x naught for all possible little x naught, and that should give you your little x naught. Okay. Do you want me to work out this formula? Should I work out this formula? Okay. Just look at the second line over there. What will be big F? Which is gradient of little x. So, the first term little r of s, that is only a function of s. So, it becomes little r prime tensor product E3. Then look at the second term, which is big R prime little x naught tensor product E3 plus big R, then del of little x naught over del x alpha tensor product E alpha, because little x naught are only functions of x1 and x2, isn't it? And then you take big R common. Then over here you will have big R transpose little r prime, big R transpose little r prime tensor product E3 plus big R transpose big R prime little x naught tensor product E3 plus del of little x naught over del x alpha tensor product E alpha. That is it. And then big R, we know it is e to the power s k, right? E to the power s k times, And what is big R transpose little r prime? That's your strain V. What is this? That's your strain K, the skew symmetric K. But then when you multiply with little x naught, it becomes its axial vector K cross little x naught, tensor product E3 plus this number. Okay, so that's what I have here. And so you have to then minimize this for all possible little x naught and find out the little x naught which minimizes its energy. But when you do this, there will be some problem. For example, it could be possible that your little x naught turns out to be such that that cross section does not have its center line at the origin, because when we do this minimization, I am not saying that please keep the center line at the origin, right. I am never saying it, I am never dictating that during the minimization. So, it is possible that your little x naught goes somewhere else, but I want, as per the kinematics, I want that its center line remains at the origin, right. The other thing could be that little x naught turns out to be such that the average orientation of the cross section is no more in the E1 E2 plane, isn't it? It could rotate somehow. That could be after the minimization. It could be that little x naught is such that the rotation is not identity. So, that again is going to violate the kinematics. Right. So, the minimization have to be done such that this kinematics is respected. Otherwise, the final energy that you will get will correspond to a rod whose V and K will be something else that what you wanted to be. Okay, I hope this point is clear. Is that clear? Okay. So, how do we set that over here? We have to put some constraints in, right, such that the kinematics is preserved. So, there are two constraints, one that the center line remains at the origin, and the other that the orientation is in the E1 E2 plane. So, let me just draw that cross section over here, maybe somewhere over here. See, what we want is it should be something like this. And we do not want that the little x naught turns out to be such that it comes over here, then the center line is no more at the origin. And further, we do not want that maybe the center line remains at the origin, but it becomes something like this, such that the orientation has changed. We do not want that to happen also. So, if we want the center line to remain at the origin, what do you think, what should be the constraint? So, the constraint to put the center line at the origin. So, constraints. So, number 1, center line at the origin. Can we write that it should be rho naught times little x dx1 dx2 equal to 0? Whatever is your little x naught, if you work out this formula, this gives you the center, the mass center of the cross section, right? And if we just set this equal to 0, then the mass center would be at the origin, isn't it? Yeah, that's a very good question. Why not the geometric center and why mass center? So that's the choice we have. We have that choice. Do we want to build our theory based on the geometric center, or we want to build a theory based on mass center, or on some other definition for center line? See, this rod theory just says we have the kinematics for a center line and the orientation of the cross section. Now, that center line could be geometric center, mass center, or some other center. So, that choice you have with you. It turns out if you keep this to be mass center, the constraints look very simple. If you put geometric center here, you can't just get rid of rho naught. You have to put some Jacobian also over here. So, the constraint becomes a bit complicated. Yes, if you, for example, want to say that let the geometric center be at the origin, then you can't just say that I get rid of this rho naught and this is the geometric center. Why not? That's because we had, maybe I'll tell you. Okay, so this is really getting little messy. So, suppose that that's my rod, and here is your cross section of S equal to 0. Okay, and take a segment of the rod which are very close to each other. So, one is at S1 and the other is at S2, for example. And this is a deformed rod. So, where is the centroid of this segment? The centroid of this segment will be simply little x dV, isn't it? Where dV is the deformed volume, right? And the domain is the deformed volume. Now, if you want to convert this into Lagrangian, this becomes little x times Jacobian into dV naught, isn't it? And you say this is the integration over the volume. So, now since this is Lagrangian volume, you could also write this as, so it is a triple integral, of course. You could also write this as first integral over S, which is going from S1 to S2, S1 to S2 of ds times the other integration over the cross section omega naught little x Jacobian d omega naught, right. And then because I want only the centroid of a cross section, then what I could do is I divide that number by S2 minus S1 and then take the limit S2 tending to S1. And which would be same as integration over omega naught of little x Jacobian d omega naught. So, we get that Jacobian here if you want the geometric center. But if you had wanted the mass center, thing would have been much easier. You know, in case of mass center, you would have rho dV, because that's your dm. So, you would have little x times dm instead of dv, but dm is rho dv, which is same as rho naught dv naught. So, that would be same as rho naught dv naught. So, you see that Jacobian does not come. So, it is nice to work with mass center. That is one advantage, that the constraint looks easier. The other advantage is when you do the dynamics, if your center line is mass center, then the kinetic energy can be broken down separately into translational kinetic and rotational kinetic separately. There will not be any coupling between translational and rotational kinetic energy. So, that is another advantage of having mass center. Okay. And you will see later on that when we extend this to a molecular rod, that constraint will have very straightforward extension instead of this geometric center constraint. Okay. So, we will have this rho naught over here. So, this is for geometric center. Okay, so this only takes care of center line at the origin, and the center line is for mass. Similarly, we also want that our orientation is such that the rotation is identity. So, how can we set that? How can we keep the orientation to be identity? Just think of this center line as some body, as some 3D body, and you want its orientation to be aligned along E1 axis, E2 axis and E3 axis. What do you think? What should you do? What about saying that the principal axis of inertia are aligned along E1, E2, E3 axis? Because when the cross section is not deformed, it is planar, its principal axis, you can choose the E1, E2 axis such that they are aligned along the principal axis of the cross section in the beginning. And then later on, then you also say when the cross section is deformed, then also the principal axis is along E1 and E2 axis only. So, if you do that, then you preserve its orientation, right. So, how can we set that the principal axis remains along E1, E2 and E3 axis? So, you have that inertia tensor, and I want the principal axis to be along E1, E2, E3 axis. How should that inertia tensor look like? the off diagonal components of the inertia tensor should be 0, right. The mixed moment of inertia should be 0. If you do that, then the inertia tensor becomes diagonal, and then its principal axis will automatically be along E1, E2, E3 axis, isn't it? So, we just have to set the mixed moment of inertia to be 0, and there are 3 of them, and you set all 3 of them to be 0. So, that brings in 3 more constraints, and you could write that in a vector form. So, integral over omega naught of rho naught, I guess I wrote it like this, rho naught x2 x3, then x1 x3, and then x1 x2 d omega naught, that is set to be equal to 0. Okay, rho naught. So, that is the x2 x3 inertia, this is x1 x3 inertia, this is x1 x2, and setting this to be 0. All right. So, these are the 2 cross sections that we want, and this is to preserve the orientation. So, vanishing of mixed moment of inertia, vanishing of mixed moment of inertia. To preserve orientation. Okay. All right. So, we have to work out the minimization under those constraints. Okay, so we set our minimization as follows. So, we have to minimize over all possible x naught. So, we have W of f plus lambda dot rho naught little x naught plus some other delta, and you can say maybe m. So, you see these are your constraints. The first constraint is from here, rho naught little x naught, and the other one is from here. This m is this number here. So, I am defining this to be your m. Okay. All right. So, that is the energy to be minimized, but then we need to get the equation for little x naught. And how do you get the equation? We just take the first variation, right. So, we take the first variation and derive the Euler-Lagrange equation. First variation to obtain Euler-Lagrange equation. And how do we take the first variation? Then you say you have little x naught epsilon is equal to little x naught plus epsilon times del x. So, maybe let us call this I. So, I of epsilon is then integral over omega naught of W of big F epsilon plus lambda dot rho naught of little x naught epsilon plus del dot m epsilon. So, that is your I epsilon, and then you want to take the first variation, which is same as setting d I epsilon over d epsilon and evaluate at epsilon equal to 0 and set this equal to 0. So that's the first variation. And how do we do that? So we go over there, integral over omega naught, and then you use chain rule for the first term, which becomes del W over del F, double contraction df epsilon over d epsilon. Plus lambda dot rho naught d little x naught epsilon over d epsilon plus delta dot, you see lambda and delta are your Lagrange multipliers. That is how we work out the minimization under constraints, plus delta dot d of m epsilon over d epsilon at epsilon equal to 0. Okay. And then we have to set it at epsilon equal to 0, all of them. This is also at epsilon equal to 0, and that's also at epsilon equal to 0. So the first term becomes, this is your first pk. So I'll write it as p, double contraction. Then we have to find this df by d epsilon, and that's your big F over here. And you are doing it for s equal to 0 cross section. So your e to the power sk just goes away, right? S equal to 0, e to the power sk is identity. And so you have to only do the variation of the term within the bracket. The first term v tensor product E3, that does not change because v is a constant, that does not change as you change your epsilon. So that drops out. The second term has got k cross little x naught. So that's your little x naught epsilon. So that has to be taken. So we have to take the derivative of that with respect to epsilon. So what do you get? So you'll get k cross, just look at here, dx epsilon over d epsilon, that simply gives you del x, right? So this becomes k cross del x, and then the third term, yes, right, k cross del x dyadic E3 plus the third term. So again over there you set your little x naught to be little x naught epsilon, and then take d by d epsilon, and that simply becomes del of del x over del x alpha tensor product E alpha. Okay, that's just the first term. Then you look at the second term plus rho naught lambda dot del x, and then you have the last term also over here, and okay, you don't have to confuse this del with this delta over here. Okay, so this is a vector delta, this is a scalar del, this is just a del, this is your Lagrange multiplier. So what does this become? Yes, so m is that whole thing over here, that integral. Well, m is without the integral. M is without the integral, just the integrand. Yes. So maybe for that particular thing we can work out separately. So d m epsilon, so we want d m epsilon over d epsilon, the same as d by d epsilon of x2 epsilon, x3 epsilon, then x1 epsilon, x3 epsilon, x1 epsilon, and x2 epsilon. So you have to use, of course, chain rule, and this becomes x2 times x2 times del x3 plus x3 times del x2, and then in the second component x1 times del x3 plus x3 times del x1, then x1 times del x2 plus x2 times del x1. And you want to write it as something times del x. So that you could do very well. I guess that would become a matrix which will be 0, x3, x2, then x3, 0, x1, x2, x1, 0 into your del x vector. Okay.
One question: the x1, 2, 3.
Yes.
The component, the coefficients of the vector x naught.
Yes, they are the components of
x naught.
x naught. Yes. So I should be having that naught also here. They are components of x naught. So x naught comma 2, x naught comma 3. So they have 1, 2, 3 components of x naught. And so they are also functions of big X1, big X2, just as x naught are functions of big X1, big X2. So their components are also functions of big X1, big X2. So you see, when we work out this, that's what we get. And this matrix, you could just call it as your big M with 2 tildes, right? M with a single tilde is this vector, and with 2 tildes is your this matrix. Okay, and when you use this, so you can come over here, and then this simply becomes plus del dot M. Okay, I don't have space here, maybe I'll write down. So it's just continues plus delta dot the matrix M into del x. Okay, you just have to do some algebra. There's nothing really here, isn't it? And you see, this M is symmetric. This M is symmetric, so you can bring it on the other side, and then it becomes M times delta dot del x, because you want to keep del x separately, right? So let's do that. Oh, rho naught is also there, yes, of course. So maybe I should write down here. Rho naught. Okay, you see the last term over here. So I moved this m on the other side and becomes m transpose, but m is symmetric, so it is same as m, and then this becomes rho naught m dot delta, rho naught m times delta, and then it is dotted with del x, because I wanted to keep my del x separately. That's why I did it. Okay. All right. So then from here also we want to take that del x separately. So we have to do some more algebra, and you see this is P tensor product, this vector tensor product E3 and its double contraction. This would be same as P E3 dot with K cross product del x. P E3 dot with K cross del x plus you come over here P double contraction, one vector tensor product the other one. So what happens is the last one comes on the other side and it becomes P E alpha dot with del of del x over del x alpha. Maybe I'll just work this out over here for a general. If you have a tensor P double contraction A tensor product B, then this is same as your P. Well, we want to prove that. So maybe if you work out in Diesel notation, this is P times Ij of Ai into Bj, because A tensor product B is Ai Bj, and we want to take the double contraction, so it becomes Pij Ai Bj, which is same as Pij Bj times Ai, and you see this is same as P matrix times the vector B and then dot with A. So the last one first gets multiplied with P and then we dot with A, and that's what we have done over here, right. The last one first gets multiplied with P, then dot the remaining vector, same over here, plus rho naught of lambda plus big M delta dot del x. Okay. And you see this is a scalar triple product, and we want to take this del x separately. So you could also write it as integral over omega naught of maybe A dot B cross C, same as A cross B dot C. Yes. So this is same as P E3 cross K dot del x, right. And this is the term where you want to do integration by parts, you want to bring this derivative on the other side. So this becomes plus del over del x alpha of P E alpha dot del x minus P E alpha dot, sorry, this is minus del over del x alpha of P E alpha dot del x. Right. So, this term breaks into two. So, you have two terms coming from here, and plus rho naught lambda plus m delta dot del x. Okay, then what we can do? Any idea what can we do now? Of course, you take the coefficients of del x together. So, this is integral over omega naught of maybe we take a minus, then del over del x alpha of p e alpha then okay, we make it a big bracket, and this I will write as k cross p3. So, that is why we get another minus sign, because I flip the cross, and so this becomes plus then. Okay. And the last one minus rho naught lambda plus m delta, and then the whole thing is dotted with del x. So, that is one term, and look at this term. You know, that is where we want to apply divergence theorem, for example. You could apply divergence theorem, p e alpha dot del x. So, maybe we will keep it separately for now. So, that is plus integral over omega naught of del over del x alpha of p e alpha dot del x. So, the whole thing has to be equal to 0. All right. Okay, we are almost there. Now, what do we do with the second term over here? As you can see, this is a divergence only in the cross section, only x1 and x2. There is no del by del x3, it is just del by del x1, del by del x2. So, how can we work this out? Yeah. P transpose del x dot E alpha. Okay. Maybe I will write it down separately here. This is integral over omega naught del over del x alpha, and you see I bring this P on the other side, and this becomes P transpose of del x dot E alpha. So, you can also bring it outside, P transpose del x dot E alpha, which is, now think of this as a vector v. So, this is same as integral over omega naught of the divergence, but only in cross section, divergence alpha of a vector v, okay, where v is P transpose del x. So, this is only divergence in the cross section, and your domain is also the cross section. And then when you apply Gauss divergence theorem, then this simply becomes integral over the boundary of the cross section del omega naught of V dot m dl, and then you put your V over here, P transpose del x, P transpose del x, and then you can bring your P transpose on the other side, and this becomes P m dot del x. So, everything looks really nice, and this is something you bring over here. So, plus integral over del omega naught. So, you replace this basically. So, I replace this with integral over del omega naught of P m dot del x. Okay. So, just few more minutes and we are done. So, look at, we have the first term over the cross section and the second term over the boundary, and you can vary your del x arbitrarily first within the cross section. So, basically the way to work out would be set both of them equal to 0, right. You have seen the argument in your continuum mechanics. So, you can set both of them separately equal to 0, and the first term, for example, this is simply the divergence in the cross section of P, which is, so this is a shorthand notation for what you have over here, plus K cross PE3 equal to rho naught times lambda plus m delta. So, that is your Euler-Lagrange equation. So, this holds in omega naught, and this is subject to that boundary condition P m equal to 0. So, that is your traction free boundary condition. And of course, they also come with your constraints, and the constraints are rho naught little x dx1 dx2 is equal to 0, and rho naught of big M dx1 dx2 equal to 0. So, that is your system of equation, and the unknowns are your little x naught, lambda and delta. That is it. So, once you solve this equation, you get your little x naught, and then your phi, the energy or the psi of v comma k, is then simply your integral over the cross section of w of big F d omega naught. So, once you get your little x naught, put that in your big F here, integrate over the cross section, that gives you your psi for your rod, 1D energy. Okay. All right. So, we will continue from here in the next class. In the next class we will, so we are just stopping here, and I will give you some comments. So, this is all about continuum. In the next class will see how to extend this theory to molecular rods. And the class will start with Prakhar. He will give lecture for maybe 1 hour, and then I'll further take on. Okay. So thank you.